How to write code for Bellman Ford algorithm. In the last two lectures, we learned about Bellman Ford algorithm. Here we are going to see how can you write code for Bellman Ford algorithm. We learned that Bellman Ford algorithm is a graph traversal algorithm which can find the shortest path from a single source vertex to all other vertices in the graph. This is what Bellman Ford algorithm does. Let us directly step into writing the code for this. We'll outline the steps first. First of all, what is the first step that we learned in Bellman Ford algorithm? We have to set the distance to source vertex as 0 because we are finding distances from the source vertex, which means source vertex is at distance 0. Distance to all other vertices should be initialized to infinity. What is the second step and the most important step is to relax all edges v minus 1 times. When I say all edges v minus 1 times, we are not going to take one edge, then relax it v minus 1 times, then move to the second edge, relax it v minus 1 times, then move to the third edge, relax it v minus 1 times. No, this is not what we are going to do. We are going to relax all edges once, then again all edges once, again all edges once, likewise v minus 1 times. This is what we'll do. What is relaxation? For any edge uv of weight w, how do you relax it? You will check whether the distance to u plus the weight of this vertex w is this value lesser than distance of v. If this is the case, what should you do? You should update distance to v as distance to u plus the weight of this vertex. This is relaxation. You will do this v minus 1 times on all edges. After that, what is the final step? It is to check for negative weight cycles. How do you check for negative weight cycles? You will again try to relax once. If it is possible to relax any edge, that is after v minus 1 relaxations, if it is possible to relax any edge, that means there is a negative weight cycle. Why it is, we had discussed in detail previously, so I'm not digging deep into it. Let's go straight into writing the code. Let us say we want to write pseudocode. We'll have a function. Let us say Bellman Ford of, what are the input parameters? You have a graph G and a source vertex S. These are the only required input parameters. After this, what is the first step? First step is we should declare the array. So practically we have seen in the illustration lecture that we need two arrays, not just one distance array. Instead, there should be two distance arrays. Why is it so? It is because we have one distance array which will take as the parent distance array. Then whatever updations we have to make in this particular relaxation, that we'll be making in another distance array by taking the first one as reference. Again, at the end of this relaxation iteration, we'll copy all the new values into the parent distance array. Again, we'll keep updating in the new distance array. This is the logic that we followed because whenever we are doing any relaxation, that should be done by considering the previous state, not the present state. Because in present state, you are still updating. These updations should be done by checking the previous state and not the present state, right? So we should have two distance arrays. We'll define both those. We'll have the first distance array, which I'll call as D1. D1 is a distance array of size, let us say V. V should be the size, whatever be the number of your vertices. And it should be all infinities. All the values should be initialized to infinity. Next step is your source vertex. That is at distance 0. You are aware of this. Because of this, what do you want to do? One more thing. You need one more distance array which is called D2. You will have D2 same as D1. It is a new distance array. Okay. Then after this, you want to initialize your source vertex in D1. I will say D1 of S, that is distance to source vertex. This should be initialized to 0. This is the only initialization you want to make. After this, you can step into the relaxation step. What do you do in relaxation? I told you v minus 1 times you have to relax all edges. So we'll have a loop which will run v minus 1 times for I is equal to 1 to v minus 1. So this loop will run v minus 1 times. Each loop, what should you do? First thing is you have D2 and D1. D1 is your existing array. We'll call it the parent array. D2 is what you are going to newly make it, and you are going to make all updations in D2. So inside the loop, first step is you should do D2 is equal to copy of D1. So I'll write D1 dot copy. In order to denote that, you should copy the contents of D1 to D2. After this, you have to pick each of the edge and do relaxation. V minus 1 times, what is the operation to be done? Each of the edge should be picked and relaxed. How do you do that? You will write for each edge, what is the edge? We'll call edges UV, which means edges from U to V. For each edge UV of, let us say, weight W, right? Weight W, what should you do? If the weight of that is W, you have to first see if this is to be relaxed. How do you check if it is to be relaxed? What did we learn in the last lecture? In order to see if this is to be relaxed, you want to see if the distance to this vertex V, UV is the edge. So if it is getting relaxed, then D1 of U, distance that is to U, plus the weight of this edge, this should be lesser than distance to V. So I'll say D2 of V. Why am I putting D2 here? I'm putting D2 because D1 is what we are already having, right? These are the previous values. But I told you all the comparisons should be done with the previous values. Then my question is, why am I putting D2 here? I'm putting D2 here because D2 is my new array. Initially, what did I do? Initially, I copied everything to D2. So as of now, I'm having before I start this loop, I'll be having same values in D1. This will be D1, same values in D2. When I'm doing this loop, I'm actually doing updations in D2. All these updations should be done by comparing with D1. The initial distance of U should always be picked from D1 because D1 is the previous state. You should not take the updated distance because then it will count as next step of relaxation. That is why. So you will be taking the old values, but when you are updating the value in D2, that is when you are finally doing this updation, the problem is sometimes you would have, let us say, already updated this value as 8 here. Okay, maybe you have done this. Then for another edge, when you are looking at it, maybe that edge is also coming to the same vertex, and if the value in D1 previously, let us say this was 12, and you found a new value here which is 10, in that case you will update this 8 to 10 if you are comparing with D1 because 10 is lesser than 12. But the point is already you have updated it with 8, which is a smaller value which should ideally stay there. In order to do this, you should compare with D2's V value, right? You understood this, right? U should always be picked from D1, but V should be verified in D2, okay? After this, what should you do? If this condition is satisfied, then you have to update the value of V. So updation is always done in D2. D2 of V, this should be equal to D1 of U plus the weight of this edge. This is the relaxation step. At the end of this loop, what should you do? You should copy all the values of D2 to D1 because D1 is going to be the parent distance array for the next iteration. For next iteration, you want again D1 to be the parent so that all these code will hold as it is. That is why here you will do D1 is equal to D2 dot copy. Okay, you are going to copy all the updated values into D1. This is the Bellman Ford algorithm. After this, we discussed one more thing. What is that? We want to check for negative weight cycles. That is, you have done this V-1 times already. After this, you have to check for negative weight cycles. How do you check for negative weight cycles? One more thing before going to negative weight cycles, there is one more concept that we discussed in the last lecture. That is, you always do not need to do this v minus 1 iterations. Sometimes it may be the case that in one complete iteration of this, one complete iteration, you may not find any changes in the D2 matrix. That is, whatever is your parent D1 matrix, the same will be your D2. We discussed that in that case, you don't have to continue. You can directly exit because your algorithm already reached the final point. It is not going to improve anymore, even if you keep relaxing edges again. So because of that, we can keep that check as well here. So before saying d1 equal to d2 dot copy, what will you say? You will say if d1 is equal to d2, if both are equal, then what should you do? You can directly return d1 here. That is, you don't have to do anything further. You can stop the algorithm here, return the d1 matrix as a distance vector. D1 or D2 both are same at this point. After this, if this is not satisfied, if this if condition is not satisfied, then you should again do this whole iteration again. So here again you will do what? D1 is equal to D2 dot copy, whatever we already discussed. After this, we have to do the check for negative weight cycle. How will you check for negative weight cycle? In order to check for negative weight cycle, we have to do one more round of relaxation. We won't do multiple relaxation, just one more round of this set of steps. Okay. So for each edge, UV with a weight W. I'll write it like this. UVW means edges UV. It is having weight W. Okay. For this edge, what are we going to do? We are going to attempt relaxation. How will you attempt relaxation? You will say if D1 of U plus weight is lesser than D2 of V. If this is the case, what does this mean? This means you are again able to do a round of relaxation. If this is possible, or here you can keep D1 as well, that's also fine because at this point D1 will be equal to D2. Okay. So if this happens, then what should you do? This means negative weight cycle detected. This means negative weight cycle detected. So what should you do in this case of negative weight cycle? You should simply return here. You can give some return value which will show failure. That is, there is a negative weight cycle in this particular graph, because of which it is not possible to find the shortest path to all the edges, all the vertices, right? Finally, if there is no negative weight cycle present, then what should you do? Then you should return whatever is your distance, D1, okay? So this is the Bellman Ford algorithm. Let us just go through this algorithm once again and then we'll do time and space complexity analysis. What did we do in this algorithm? Initially, we initialized a distance vector D1 of size V in which all the values will be infinity. Then we had one more distance vector D2 which is same as D1. After that, we initialized the source vertex as 0. Then we started the loop for relaxation. V minus 1 times we are running this loop. First step is to copy all the values in D1 to D2. Then we'll relax each of the edge. For each edge UV, which is of weight W, what are we doing? We are doing relaxation here. If D1 of U plus W is less than D2 of V, then we'll update the new value in D2. In case D1 is same as D2, that means that is at the end of this iteration, if D1 is same as D2, that means there is no updation done this time when we relaxed all the edges once. Hence, you can stop Bellman Ford algorithm here. Your final distance vector is found. That is the shortest paths. If it is not, then you again have to copy D2 to D1 and continue this iteration again and again. Maximum V minus 1 times. Finally, you have to do a check for negative weight cycle. For each edge UV of weight W, what will you do? You will attempt to do one round of relaxation. If you are successful, that means negative weight cycle is present. You will directly return from here saying it is not possible to find the shortest path because there is a negative weight cycle in the graph. In case there is no negative weight cycle, then you can return distance vector d1 as your final output of Bellman Ford algorithm. Then the question is, what are the time and space complexities here? Let us see what contributes to time and space complexities. First thing, there is a loop here which is running v minus 1 times. So here these initializations, these are just simple vectors. So d1 is of size v, initializing, let us say, will take order of v. Similarly, d2 is also having same initialization, maybe order of v here as well. But this particular loop, it is going to run order of v times. In each of the loop, we are again running this loop, which is going to run for all of the edges. So order of e times. For all of the edges, we are going to run this loop. What does that mean? That is the total. This is all order of 1 computation. These are all order of 1. So at the end of this, we know there are 2 loops. One outer loop which is running order of v times. Inside that, there is an inner loop which is running order of e times, which means the time complexity of your algorithm is order of v into e. Order of ve is the time complexity of Bellman Ford algorithm. What about the space complexity? Space complexity, the additional space you are taking is for the distance vectors d1 and d2 here. In case of d1 and d2, both of them are of size v, which means your space complexity is order of v. So your time complexity of Bellman Ford algorithm is order of ve, and your space complexity is order of v.